Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 3, Projectivities of the Primitive Geometric Forms of 1, 2, and 3 Dimensions. Section 23, The Projectivity of a One-Dimensional Primitive Forms. The projectivity of one-dimensional primitive forms will be discussed with reference to the projectivity of pencils of points. The corresponding properties for the other one-dimensional primitive forms will then follow immediately by the theorems of duality. Theorems 11 through 13 of Chapter 1. Theorem 1. If A, B, and C are 3 points of a line L, and A', B', C', 3 points of another line L', then A can be projected into A', B into B', and C into C' by means of 2 centers of perspectivity. The lines may be in the same or in different planes. Assumptions A and E. Proof: if the points in any one of the pairs A', B', or C' are coincident, one center is sufficient, namely the intersection of the lines determined by the other 2 pairs. If each of these pairs consists of distinct points, let S be any point of the line A', distinct from A and A'. Figure 22. From S, project A, B, and C on any line L', distinct from L and L', but containing A' and a point of L. If B', C' are the points of L', corresponding to B and C, respectively, the point of intersection S' of the lines B', B', C', C', is the second center of perspectivity. This argument holds without modification if one of the points A, B, or C coincides with one of the points A', B', C' other than its corresponding point. Corollary 1. If A, B, C, and A', B', C' are on the same line, 3 centers of perspectivity are sufficient to project A, B, C into A', B', C', respectively. Assumptions A and E. Corollary 2. Any 3 distinct elements of a one-dimensional primitive form are projective with any 3 distinct elements of another or the same one-dimensional primitive form. Assumptions A and E. For when the 2 forms are of the same kind, the result is obtained from the theorem and the first corollary directly from the theorems of duality. Theorems 11 through 13 of Chapter 1. If they are of different kinds, a projection or section is sufficient to reduce them to the same kind. Theorem 2. The projectivity ABCD projected to BADC holds for any 4 distinct points A, B, C, D of a line. Assumptions A and E. Proof: from a point S not on the line L equal to AB, project ABCD into A, B', C', D' on a line L' through A and distinct from L. Figure 23. From D, project A, B', C', D' on the line SB. The last 4 points will then project into BADC by means of the center C'. In Figure 23, we have ABCD is perspective with center S, with A, B', C', D' is perspective with center D to B, B', C', S, is perspective with center C' with BADC. It should be denoted that a geometrical order of the points A, B, C, D has no bearing on the theorem. In fact, the notion of such order has not yet been introduced into our geometry, and indeed cannot be introduced on the basis of the present assumptions alone. The theorem merely states that the correspondence obtained by interchanging any 2 of the 4 collinear points, and also interchanging the remaining 2, is projective. The notion of order is, however, implied in our notation of projectivity and perspectivity. Thus, for example, we introduce the following definition. Definition: 2 ordered pairs of elements of any one-dimensional form are called a throw. If the pairs are AB, CD, this is denoted by T of AB, CD. 2 throws are said to be equal provided they are projective. In symbols, T of AB, CD is equal to T of A prime B prime, C prime D prime, provided we have A, B, C, D is projective with A prime, B prime, C prime, D prime. The last theorem then states the equality of throws. The throw AB, CD is equal to the throw BA, DC is equal to the throw CD, AB is equal to the throw DC, BA. The results of the last theorem may be stated in the following form. Theorem 1 prime. If 1, 2, 3 are elements of any one-dimensional primitive form, there exist projective transformations which will effect any one of the 6 permutations of these 3 elements. Theorem 2 prime. If 1, 2, 3, 4 are any 4 distinct elements of a one-dimensional primitive form, there exist projective transformations which will transform 1, 2, 3, 4 into any one of the following permutations of itself: 1, 2, 3, 4, 2, 1, 4, 3, 3, 4, 1, 2, 4, 3, 2, 1. A projective transformation has been defined as the resultant of any sequence of perspectivities. We proceed now to the proof of a chain of theorems which lead to the fundamental result that any projective transformation between 2 distinct one-dimensional primitive forms of the same kind can be obtained as the result of 2 perspectivities. Theorem 3. If P, P prime, and P double prime are pencils of points on 3 distinct concurrent lines L, L prime, L double prime, respectively, such that P is perspective with center S with P prime, and P prime is perspective with center S prime to P double prime, then likewise, P is perspective with center S double prime to P double prime, and the 3 centers of perspectivity S, S prime, and S double prime are collinear. Assumptions A and E. Proof: let O be the common point of the lines L, L prime, L double prime. If P1, P2, and P3 are the 3 points of P, and P1 prime, P2 prime, P3 prime, and P1 double prime, P2 double prime, P3 double prime, the corresponding points of range P prime and range P double prime. Figure 24. It is clear that the triangles P1, P1 prime, P1 double prime, P2, P2 prime, P2 double prime, P3, P3 prime, P3 double prime are perspective from O. By Desargues' theorem, Theorem 1 of Chapter 2, homologous sides of any pair of these 3 triangles meet in collinear points. The conclusion of the theorem then follows readily from the hypothesis. Footnote: if the points in each of these sets of 3 are collinear, the theorem is obvious and the 3 centers of perspectivity coincide. Corollary: if n concurrent lines L1, L2, L3, Ln are connected by perspectivities, the range P1 is perspective with center S12 to the range P2, is perspective with center S23 to the range P3, is perspective with center S34, is perspective with center Sn-1n to the range Pn. And if L1 and Ln are distinct lines, then we have the range P1 perspective with the range Pn. Assumptions A and E. Proof: this follows almost immediately from the theorem, except when it happens that a set of 4 successive lines of the set L1, L2, L3, Ln are such that the first and third coincide, and likewise the second and fourth. That this case forms no exception to the corollary may be shown as follows. Consider the perspectivities connecting the pencils of points on the lines L1, L2, L3, L4 on the hypothesis that L1 is equal to L3 and L2 is equal to L4, figure 25. Let L1, L2 meet in O, and let the line S12, S23 meet L1 in A1 and L2 in A2. Let A3 equal A1 and A4 be the corresponding points of L3 and L4 respectively. Further, let B1, B2, B3, B4, and C1, C2, C3, and C4 be any other two sequences of corresponding points in the perspectivities. Let S for 1 be determined as the intersection of the lines A1, A4 and B1, B4. The two quadrangles S12, S23, B2, C2, and S41, S34, B4, C4 have 5 pairs of homologous sides meeting L1, which is equal to L3, in the points O, A1, B1, B3, C3. Hence the side S41, C4 meets L1 in C1 by Theorem 3 of Chapter 2. Theorem 4. If the ranges P1, P2, P are pencils of points on distinct lines L1, L2, L, respectively, such that the range P1 is perspective through center S1 with P is perspective through center S2 with P2, and if the range P' is the pencil of points on any line L' containing the intersection of L1 and L, and also a point of L2, but not containing S2, then there exists a point S1' on S1, S2, such that the range P1 is perspective through S1' with the range P', which is perspective through S2 with the range P2. Assumptions A and E. Proof. Clearly we have the range P1 is perspective through center S1 with the range P is perspective with center S2 to the range P' is perspective with center S2 with the range P2. But by the preceding theorem and the conditions on L', we have the range P1 is perspective through S1' with the range P', where S1' is a point of S1, S2. Hence we have the range P1 is perspective with center S1' with the range P', which is perspective with center S2 with the range P2. This theorem leads readily to the next theorem, which is the result towards which we have been working. We prove first the following lemmas. Lemma 1. Any axial perspectivity between the points of two skew lines is equivalent to and may be replaced by two central perspectivities. Assumptions A and E. For let the ranges P and P' be the pencils of points on the skew lines. Then if S and S' are any 2 points on the axis S of the axial perspectivity, the pencil of lines S P, S' P' are so related that pairs of homologous lines intersect in points of the common line to the planes of the two pencils S P and S' P'. Since each pair of homologous lines lie, by hypothesis, in the plane of the axial pencil S P equal to S of P'. Lemma 2. Any projectivity between pencils of points may be defined by a sequence of central perspectivities. For any non-central perspectivities occurring in the sequence defining a projectivity may, in consequence of lemma 1, be replaced by sequences of central perspectivities. Theorem 5. If two pencils of points, P and P', on distinct lines are projective, there exists a pencil of points Q and 2 points S, S', such that we have the pencil of points P is perspective with center S to the pencil of points Q is perspective with center S' to the pencil of points P'. Assumptions A and E. Proof by hypothesis and the two preceding lemmas, we have a sequence of perspectivities. Pencil of points P is perspective with center S1 to the pencil of points P1 is perspective with center S2 with the pencil of points P2 is perspective with center S3 with the pencil of points P3 is perspective with center S4 ... is perspective with Sn to the pencil of points P'. Footnote: given a class of elements P, the symbol S P is used to denote the class of elements SP determined by a given element S and any element of P. Hence, if P is a pencil of points and S is a point not in P, SP is a pencil of lines with center S. If S is a line not on P, S of P is a pencil of planes with axis S. We assume the number of these perspectivities to be greater than 2, since otherwise the theorem is proved by applying the corollary of Theorem 3. When necessary, this sequence of perspectivities may be so modified that no 3 successive axes are concurrent. We may also assume that no 2 of the axes L, L1, L2, L3, L prime of the pencils P, P1, P2, P3, P prime are coincident. For Theorem 4 may evidently be used to replace any Lk equal to Li by a line Lk double prime not equal to Li. Now let L1 prime be the line joining the points L1 and L2, L3, and let us suppose that it does not contain the center S2, figure 26. If then P1 prime is the pencil of points on L1 prime, we may, by Theorem 4, replace the given sequence of perspectivities by P, perspective with center S1 prime to P1 prime, perspective with center S2 to P2, perspective with center S3 to P3, perspective with center S4, And this sequence may in turn be replaced by P, perspective with center S1 prime to P1 prime, perspective with center S3 prime to P3, perspective with S4, by Theorem 3. If S2 is on the line joining LL1 and L2, L3, we may replace L1 by any line L1 double prime through the intersection of L1, L2, which meets L and does not contain the point S1, by Theorem 4. The line joining L2, L3 to L1 double prime does not contain the point S2 double prime, which replaces S2. For since S2 is on the line joining L3, L2 to LL1, the points L3, L2, and LL1 are homologous points of the pencils P3 and P. And if S2 double prime were on the line joining L3, L2 to LL1 double prime, the point L3, L2 would also be homologous to LL1 double prime. We may then proceed as before. By repeating application of this process, we can reduce the number of perspectivities one by one until finally we obtain the pencil of points Q, and the perspectivities P is perspective with center S to Q, which is perspective with center S prime to P prime. As a consequence, we have the important theorem. Theorem 6. Any two projective pencils of points on skew lines are axially perspective. Assumptions A and E. Proof: the axis of perspectivity is the line SS prime of the last theorem.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.